Now let's talk about a table representation of a 3D function, because we've already talked about the graphical, right? And we've already talked about the function. Now, sometimes we're going to need to have tables of values, just like in any other function where we had maybe y equals x squared. When you were learning these for the first time, your teacher would say, all right, let's make a table of values where we have where we have x's and y's. We'd say we'd substitute in 0, get out 4, or actually in this case we get out 0, and then we sub in 1, we get out 1, sub in 2, get out 4, and so on and so forth. And it always hinged upon which one was your independent variable and which one was your dependent. And you would substitute numbers in for your independent variable and then use your equation to get at values for your dependent. Well, a table of values in 3D is not very different, except we had multiple independent variables instead of just one. So when you have a 3D graph, this is one way of representing a table of values. Now notice what I've done is use the x values, say this row here is my x values, and then my y's are going down. So this column here are my y values. So what this is saying is when I substitute in 1 or 2 or 3 or 4 or 5 for x, I'm going to get certain values, but they have to get paired up with other y values. So for example, let's look at the value of this value right here, this one I just highlighted in green. This would mean when I substitute in 1 for x, 6 for y, I'm going to get out 6 for z. Now notice, instead of ordered pairs, we have ordered triplets. So an x, a y, and a z value all go together. And you just say, what were my two independents? What was my x and my y? That was 1 and 6. What was my z? Well, that was the green value. That was 6. So the idea here is everything in here, all of these values that I'm highlighting in green, these are your z's. These are all of your outputs. Right? So the borders are your input variables, and the main chunk of your table, that's all your output variables. Right? So let's pick one more. Let's pick one more. Let's make sure we're getting this. Let's do this value right here. Okay, what is that one saying? Well, when the x value is 4 and the y value is 6, my z value is 7. And I would write that as an ordered triplet, so it's 4, 6, 7. There we go. All right, now, another fun thing we're going to do later is looking for maximums and minimums. And it's really easy to do. What we're going to do when we're looking at a table, what we're going to do is just look at each row, row by row, and we're going to say, what's happening? Are my numbers going up or are they going down? So don't overthink that. It's going to come up later in another section, but just start playing with that idea right now, saying, okay, well, I'm holding 4 constant. I'm letting my x's change. So 4 went to 4, then 5, then 6, then 5, then... Oh, wait, there's a maximum right there. That's as high as it went. 5, then 6, then 7. Oh, then 6, then 5. There's another maximum. And so you can see my maximums are occurring in this row, in this column. Now, how about my rows? 4, then 5, then 6, then 5. Oh, there we go. There's a maximum there. All right, here we go. Actually, I shouldn't use yellow because I already used yellow. Let me use purple. Then we have 5, 6, 7, 6. Oh, there we go. 6, 7, 8, 7. Oh, right there. 5, 6, 7. Oh, right there. Right there. So now when we get to maximums, we're going to say, there it is, because that's where the two meet. Again, not happening yet, but I just wanted, since I have the table on the page and I have you guys looking at it, I wanted you to start looking at it a little deeper than just worrying about x and a y and a z. I wanted you to start looking for change. How are these things moving from across a row or across a column? And if that kind of went over your head, don't worry. We're going to come back. We're going to do it a little bit later. We're going to combine it with some calculus techniques, and hopefully it'll be a little easier then. Okay? Now, one thing that we are going to focus on, just like when you started learning functions, you started with lines. We're going to start with lines as well. I want you to think about lines. So, back in the day, when you looked at this equation, y equals 2x plus 4, is that a linear equation? Well, yeah, you look at it and you're saying, of course, but why is it a linear equation? How do you look at this and know? Well, the exponents on all of my variables are all raised to the first power, and none of my variables are multiplying each other. So a very easy way to kind of make that argument is saying, well, because I've had students in the past say, well, if they're linear, if the variables are 1, then they're linear. If they're raised to the first, then they're linear. Well, look at this. If I write it as x times y equals 4, is that a linear function? Well, no, because we have these two variables multiplying each other, and if you solved for y, you would end up with y equals 4 divided by x, and this is clearly not a linear function. If you remember, this function looks something like that. That's not linear, that's not a line. So, definitely doesn't have a constant slope. All right, so is this function linear? Yes. What are we looking for? All of my variables have exponents of 1, and they are not multiplying each other. So similarly, when we go to 3D, we use the same logic. Are all of my variables raised to a first power? So looking at this next equation here, my x is raised to a first, my z is raised to the first, and do I have any variables multiplying each other? No, no, I don't have anything multiplying, so therefore it is linear. We're good to go. Okay, so you take a look at this next one and decide, is this third one linear? Yeah, it is. All right, I may have gone too fast for you, but I apologize. I'm just getting so excited. I love linear equations. Okay, if I could write the word linear, it'd be even better. All right, now for the next one, pause the video, take a think, take a thought. Okay, here we go. Um, are all of my variables raised to a first power? Absolutely they are. But are any variables multiplying each other? Absolutely they are. And of course this is not linear, because if we just wrote it this way, it'd be kind of obvious. X times x is x squared. Yeah, no, this isn't linear. Not linear. Now, and there you go. Um, and now the next thing you're going to see is we're going to talk about linear. Is there an interaction, or is it neither? This one would be neither. Now you might be saying, well, how do I know if there's an interaction? Well, that's what we'll talk about on the next one. So here, so it's not linear, it's not an interaction. This is a neither, it's neither of the two. All right, so now the next one. Variables raised to the first power, right? But we have multiplication. So you might be saying, but I can't combine like the last problem. The last problem was x times x, which made x squared. I can't do x times y. So isn't this linear? No, it's not linear for the same reason that, oh, I already erased it, but for the same reason that this one was not linear. Okay, but what we're going to end up calling this here is this is going to be called a inner action. This is a function where you have an x and a y multiplying each other, so therefore they're having an interaction on each other, which makes our graph not linear. Now, if you want to, go graph this. Go put that in that 3D grapher tool, and you will see it is not linear. It's going to have a curve to it. And what does a linear function look like in that 3D grapher? Go back and graph this one. And what you'll see is what we don't really refer to them as lines, we refer to them as planes. So you can think of them as walls that travel through space and never end. Okay, so this is an interaction term. And if you were to think about the exponents that are multiplying, it's an x to the first times a y to the first. And what we're going to do is we're going to describe that as a second degree, because 1 plus 1 makes 2, right? And it's kind of like, it's the same logic as x times x makes x squared. If these were the same variable, they would be squared, so it's a second degree. All right, so this next one, I want you to try this one on your own. I want you to determine, is it linear? Is it interaction? And if it is an interaction, what degree is it? Okay, and then, or is it neither? All right, pause the video, give it a shot. All right, here we go. So what have we come up with here? Well, hopefully you came up with it is a interaction because there are two different variables multiplying each other, and it is of the third degree. All right, now, what are we going to do next? Let's just finish this up. Let's get to the thing that we all dread. Let's get to word problems. Okay, now, I want you to remember what we're doing in here. All this word problem stuff in this section, This is all just input output. This is just put in a number, get out a number. There's no derivatives. There's no calculus. This is the equivalent of intermediate algebra, or even easier than that, maybe beginning algebra, where but where we're just going to be talking about slope of lines and that kind of stuff. Okay, so your cost of producing lemonade for a stand is outlined by this function below, where L is the number of lemons used, S is the sugar in pounds, and W is the amount of water used in gallons. All right. Now, do you guys remember from calculus marginal cost? What does marginal cost mean? Well, if you remember, that's the change in cost per change in one, well, not even per change in, per one unit. So in this case, it's lemons. So it's the change in cost per lemon. Now, why am I telling you that it's 15 cents? Well, I want you to realize that when we see this function, first of all, is it a linear function? Is it an interaction function? Or is it neither? All right. Well, if you're thinking about it, you say, all right, my L is to the first degree, my S is to the first power one, my W is to a power one. Hey, this thing's a linear function, and what we know about linear functions is they have constant slope. So think about slope. Think about slope. We're used to having slope as change in y over change in x, right? Well, that really stemmed from dependent variable divided by independent variable, right? Well, so in this case, what are we looking at here? In this function, I have three independent variables, but this slope is only related to lemons. So if I'm looking at this slope right here, this is change in L over change in, now what is sorry, try again. My bad. Change in blank over change in L, right? It's dependent over independent. Now, what is my independent variable? L. What is my dependent variable? C. So therefore, what this 15 cents is talking about is change in cost per change in lemon, and in particular, one lemon. So you can therefore determine every lemon is costing me 15 cents. So what I want you to do now is determine what is the slope of this line, of this part. Sorry. Well, all right, what's the value? What's the number in the front? It's a 1, right? So therefore, now talk about the change. This is change in, sorry, not D, wrong D. Change in over change in. Okay, what is my dependent variable? Well, that's not changing. It's still cost. What is my independent variable? That is S. So what we are saying here is my sugar, the change in cost per sugar, and sugar was measured in pounds. So my cost for 1 pound of sugar is $1. Cool. All right. So similarly, again, 0.001. This is measured in, again, cost, so this is measured in dollars. So this is a less than a penny, a tenth of a cent. Is what are the units on it though? It's dollars per gallon of water, because my output is cost, my input is water, gallons of water. Cool. All right. So when you're going through the homework, just keep all this linear stuff in mind. Think about slope the old-fashioned way, right? Think about if I see something like C of 10, comma 0.5, comma 1, what does that mean? Everywhere I have an L, replace it with a 10. Everywhere I have an S, replace it with a 0.5, and so on and so forth. All right, so we already talked through this. What is the marginal cost of sugar and water? The sugar was, there we go. Sugar was $1 per pound, and water was very, very inexpensive, but water tends to be that way in our country. $0.001, or 1/10 of a cent per gallon. Units are crazy important. All right, so for this one, what would this mean? All right, so C of 10, comma 0.5, comma 1 is equal to 0.15 times 10 plus sugar, which I just said I'm going to use half a pound of sugar, plus 0.001 times 1. And you figure that out, and you'll figure out your cost for making this recipe of lemonade. I have no idea if it's good or bad. I just made these numbers up. Someone let me know. Make it. It's half a pound of sugar and 10 lemons. I'm sure it's going to be very interesting tasting. And yes, and 1 gallon of water. So 1 gallon of water with 10 lemons and a half a pound of sugar. Please enjoy. All right. Anyway, so I hope this helps. I hope you enjoyed this lesson. I know I did. Write your summary, and I'll see you in the next lesson.